Tonight, we are going to tell the oldest story we know. It is the story of the light that wakes you in the morning, the warmth that feeds the forests, and the gravity that holds the Earth in its orbit. We are going to explore the birth of the sun. But before we drift back into the deep time of the galaxy, I invite you to subscribe to this channel and perhaps leave a comment below. Tell us where you are listening from tonight and what time it is in your part of the world. It is a way to anchor ourselves in the present before we lose ourselves in the vastness of the past. Now, let your body settle. Let the artificial lights of your room fade from your mind. We are going to a place of absolute darkness. We are traveling back 4.6 billion years to a quiet corner of the Milky Way galaxy. To understand the sun, we must first understand the nothingness from which it came. We must erase the solar system. There is no Earth here. There is no Mars. There is no Jupiter. There is not even a central star to anchor them. There is only a cloud. We call this the solar nebula. It is a giant molecular cloud, a vast structure of gas and dust floating in the interstellar medium. It is colossal. It stretches for dozens of light years across the spiral arm of the galaxy. If you could see it from the outside, it would look like a dark, ragged hole in the starry background, blotting out the light of the stars behind it. But we are going inside. We are drifting into the mist. Inside the nebula, it is silent. It is a silence deeper than any quiet we can experience on Earth. It is the silence of a vacuum, where sound cannot travel because the atoms are too far apart to touch. It is a stillness that has lasted for millions of years. It is also cold. The temperature here is only 10 degrees above absolute zero. It is minus 263 degrees Celsius. In this crushing cold, thermal energy is almost non-existent. The atoms are sluggish. They move with a slow, lazy drift, barely possessing the energy to rotate. This cold is essential. If the cloud were warm, the atoms would be moving fast. They would have high pressure. They would push outward, dispersing the cloud into the void. But because it is cold, the gas creates very little pressure. It allows the cloud to hang together. It allows gravity to have a chance. Let us look at the ingredients of this cloud. It is the raw material of everything we know. It is 98% gas, mostly hydrogen, the primordial element formed in the Big Bang, and helium, its inert cousin. These are the fuels that will one day power the star, but the remaining 2% is dust. In astronomy, dust does not mean the gray fluff you find under your bed. It means tiny, solid grains of heavier elements: carbon, silicon, oxygen, iron, gold. Where did this dust come from? It is the ash of dead stars. Before our sun was born, other generations of stars lived and died in this region of the galaxy. They fused hydrogen into heavier elements in their cores, and when they exploded as supernovae, or puffed off their outer layers as red giants, they scattered these precious elements into the void. These atoms drifted through space for eons. In the cold of the molecular cloud, they froze. They clumped together. Silicon atoms found oxygen atoms and formed silicate grains, microscopic rocks. Carbon atoms clicked together to form graphite and soot. Water molecules froze into ice crystals, coating the dust grains in a layer of frost. So the cloud is a mixture of ancient gas and recycled stardust. Every atom of carbon in your body, every atom of iron in your blood was once floating here. in this dark, freezing mist, waiting for a new home. We are currently drifting in the pre-solar graveyard, which is about to become a nursery. For a long time, nothing happens. The cloud is in hydrostatic equilibrium. This is a fancy way of saying it is balanced. Gravity wants to pull the cloud inward. Every atom pulls on every other atom. The center of the cloud pulls on the edges. Gravity wants to crush the cloud down into a single point, but gas pressure wants to push the cloud outward. Even at these low temperatures, the atoms are moving slightly. They bump into each other. They exert a faint outward force. There is also magnetism, weak magnetic fields threading through the gas, acting like springs, resisting the collapse. Also, the cloud is turbulent. It swirls and eddies, and this motion keeps it puffed up. For millions of years, these forces cancel each other out. The inward pull equals the outward push. The cloud hangs in the sky, a stable, dark sculpture. It is a reservoir of potential, but it needs a push. It needs a trigger. We do not know exactly what the trigger was for our sun, but the forensic evidence locked inside meteorites gives us a clue. About 4.6 billion years ago, a massive star nearby reached the end of its life. It was a Wolf-Rayet star, or perhaps a blue supergiant. It collapsed and detonated in a supernova explosion. This explosion released a tsunami of energy. A shock wave traveled through the interstellar medium at thousands of kilometers per second. It swept up the gas in its path, creating a dense shell of material. This shock wave hit our quiet, stable molecular cloud. It slammed into the side of the nebula. It did not destroy it. It compressed it. The shock wave squeezed the gas. It pushed the atoms closer together. Suddenly, the density in a specific region of the cloud spiked. The atoms were packed tight. This increase in density tipped the scales. The balance was broken. Gravity, which depends on distance, suddenly became much stronger because the atoms were closer. The outward pressure could no longer hold back the inward pull. The region became genes unstable. This is the critical point in astrophysics where a cloud becomes too heavy to hold itself up. It begins to fall. The collapse begins. It is not an explosion, it is an implosion. It is a landslide of gas. Imagine a region of the cloud, perhaps a light year across. This region contains enough mass to make 1,000 solar systems. As gravity takes hold, this region fragments. It breaks into smaller clumps. One of these clumps, a pre-solar course, is destined to become us. Let us focus on this single core. It is a sphere of dark gas roughly 100 times the size of our current solar system. It is isolated from the rest of the nebula. It has its own gravity now. It is a world unto itself. At first, the collapse is slow. The gas drifts inward at a leisurely pace. If you were watching, you wouldn't see movement. You would just notice that over thousands of years, the cloud is getting smaller and darker. But gravity is an accelerating force. The closer the atoms get to the center, the stronger the pull. The stronger the pull, the faster they fall. The drift becomes a flow. The flow becomes a rush. Billions of tons of hydrogen and helium are streaming toward the center of the core. They are falling freely through the void. As they fall, they carry something with them: spin. The original nebula was not perfectly still. It had a tiny, imperceptible rotation, perhaps caused by the turbulence of the galaxy itself. As the cloud shrinks, this rotation speeds up. This is the conservation of angular momentum. It is the same law that makes an ice skater spin faster when she pulls her arms in. The cloud is pulling its arms in. A cloud that took 1,000,000 years to rotate once might now rotate once every 1,000 years, then every 100, then every 10. This spin changes the shape of the collapse. Gravity tries to pull everything into a sphere, but the spin creates a centrifugal force that pushes outward at the equator. Material falling from the top and bottom, from the poles, can fall straight to the center. There is nothing to stop it, but material falling from the sides feels the spin. It is flung outward. The sphere flattens. It transforms into a disk, the protoplanetary disk. This is why our solar system is flat. This is why all the planets orbit in the same plane, in the same direction. We are living on the fossilized remnants of that initial spin. But let us look at the center. In the middle of the disk, where the material from the poles is crashing down, the density is skyrocketing. The atoms are crowding together. They are bumping into each other. In the open cloud, a collision was rare. Now, it is constant. Every time an atom hits another atom, it transfers energy. The kinetic energy of the fall, the speed of the gas, is turned into thermal energy, heat. The center of the cloud begins to warm up. It rises from -260 degrees to -200, then to -100. It is still freezing by human standards, but for the cloud, it is a heat wave. For a long time, this heat can escape. The cloud is transparent to infrared light. The heat generated by the collisions simply radiates away into the cold of space. The core stays cool, allowing it to collapse further. But eventually, the density becomes too high. The gas becomes too thick. The heat can no longer escape. The infrared photons get trapped, bouncing around inside the thickening fog. This is a critical threshold. The core becomes opaque. It creates a greenhouse effect. The heat is trapped inside. The temperature spikes violently. In the center of the disk, a ball of hot gas forms. It is no longer collapsing freely. The pressure of the trapped heat is pushing back against gravity. It stabilizes. A protostar is born. This is the infant sun. It is huge, much larger than the sun today. It is bloated and red. It does not shine with the nuclear fire. Fusion has not started yet. It shines only with the heat of its own compression. It glows like a dying ember, but in reverse. It is an ember that is getting hotter. The protostar is surrounded by a shroud of dust. It is cocooned in its own birth cloud. If you were outside the nebula looking in, you wouldn't see the star yet. You would only see a dark, warm blob in the infrared. But inside the cocoon, the environment is chaotic. Material is still raining down onto the surface of the protostar. It falls from the disk, spiraling inward, crashing onto the star in fiery shockwaves. The star is eating. It is gathering mass. It is growing from a small seed into a giant. This phase creates a powerful wind. The magnetic fields of the young star are twisted by the rotation. They launch jets of gas from the north and south poles. These bipolar jets shoot out into space for light years. They are like the cries of the newborn star. They clear away the surrounding gas. They punch a hole in the cocoon. Through these holes, the first light of the sun escapes into the galaxy. It is not the steady yellow light we know. It is a flickering, violent, reddish light. The young sun is temperamental. It flares. It spots. It varies in brightness by the hour. But deep inside, in the core of the protostar, the real work is just beginning. The temperature is climbing. 2,000 degrees, 10,000, 100,000. The atoms are moving faster and faster. They are shedding their electrons, turning from a neutral gas into a plasma, a soup of charged particles. But it is still not hot enough. To ignite a star, you need millions of degrees. You need to overcome the electric repulsion between protons. You need to force the universe to do something it doesn't want to do. Fuse matter. Gravity is patient. It continues to squeeze. The protostar shrinks. As it shrinks, the potential energy transforms into more heat. It is a slow, grinding compression. This phase, the T Tauri phase, lasts for millions of years. The sun is fully formed in terms of mass, but it hasn't turned on its main engine yet. It is like a car coasting downhill, engine off, lights on, powered only by gravity. Around the star, the disk is evolving too. The dust grains are colliding, sticking together, forming pebbles. The pebbles form boulders. The boulders form planetesimals. The planets are being born in the dark, circling the glowing red furnace in the center. But they are waiting for the moment of ignition. They are waiting for the star to wake up. Let us pause here in this twilight era. The solar system is a swirling disk of dust and fire. The sun is a red giant child, bloated and turbulent. The planets are rocky seeds hiding in the smog. It is a time of violent potential. The piece of the molecular cloud is gone. The structure has been shattered by gravity. But a new order is emerging. The chaos is organizing itself. The spin has created a plane. The gravity has created a center. The heat has created a gradient, hot in the middle, cold at the edges. This gradient will decide the destiny of the planets. Rock and metal will survive near the heat to build the Earth. Ice and gas will survive in the cold to build Jupiter. The layout of our home is being dictated by the warmth of the protostar. As we watch the young sun contract, we are witnessing the ultimate act of recycling. The atoms in the core, the hydrogen protons, have been around since the first second of the Big Bang. They have drifted through the universe for 9 billion years. They have passed through other galaxies, other clouds. Now, they are being gathered into a space smaller than the Earth. They are being pressed together. They are about to end their long journey as individuals and become something else. They are about to become light. The dust in the disk, the silicon, the carbon, was forged in the final moments of ancient stars that no longer exist. It has traveled across the spiral arm to be here. Everything in this swirling cloud has a history, and everything has a future. The sun is the gathering place. It is the hearth where the universe comes to warm itself. In the next chapter, we will dive into the core. We will follow the temperature as it climbs past the critical threshold. We will see the moment when gravity finally squeezes hard enough to overcome the electromagnetic force. We will see the strong nuclear force snap 2 protons together. We will witness the ignition of fusion. The moment the sun stops shrinking and starts shining. The moment the star truly comes alive. We will explore the proton-proton chain, the specific reaction that powers our world. And we will see how the onset of fusion changes the entire solar system, blowing away the dust and clearing the view. But for now, rest in the warmth of the protostar. The light is dim and red, like a dying fire. But it is actually a fire that is just catching. The long night of the nebula is over. The dawn is coming, not a dawn of a single day, but a dawn that will last for 10 billion years. You are floating in the dust that will one day become the ground you walk on. You are bathed in the infrared glow of the star that will one day light your sky. You are present at the beginning. We have stood in the silence of the molecular cloud, watching the dust of dead stars drift in the cold void. We have seen the shock wave from a distant supernova ripple through the dark, disturbing the sleep of the nebula. The balance has been broken. The gravity of the gas has overcome its internal pressure. The great collapse has begun. To understand what happens next, we must shift our perspective from the static to the kinetic. We are no longer looking at a painting. We are watching a landslide. But this is a landslide that happens in slow motion over hundreds of thousands of years on a scale that dwarfs the imagination. It is the falling of the sky. Imagine a region of the cloud, roughly 1 light year across. This is the pre-solar core. It contains all the atoms that will eventually make up the Sun, the Earth, Jupiter, and your own body. At this moment, they are spread out over 9 trillion kilometers. They are lonely, separated by vast gulfs of emptiness. But gravity is a relentless summoner. It calls to every atom. Come closer, it whispers, and slowly the atoms obey. They begin to drift toward the center of mass. At first, the movement is imperceptible, a few meters per second. But gravity is an accelerating force. The closer the atoms get to the center, the stronger the pull becomes. The stronger the pull, the faster they fall. The drift becomes a stream. The stream becomes a rushing river of gas. Billions of tons of hydrogen and helium are falling freely through the void, racing toward a central point. As they fall, they trade their position for speed. They convert gravitational potential energy into kinetic energy. They are waking up from their long, cold sleep. But they do not fall in a straight line. The original cloud was not perfectly still. It had a tiny, almost unmeasurable rotation, perhaps just a slight turbulence left over from the swirling of the galaxy itself. As the cloud shrinks, this rotation does not disappear. It is amplified. This is the law of conservation of angular momentum. It is one of the fundamental rules of the universe. It is the same physics that makes an ice skater spin faster when she pulls her arms in. The cloud is pulling its arms in. It is shrinking from a size of light years to the size of a solar system. To conserve the total spin of the system, the speed must increase. The lazy drift turns into a slow rotation. The slow rotation turns into a rapid whirl. The core of the cloud begins to spin faster and faster. This spin has a profound effect on the shape of the emerging system. Gravity wants to pull everything into a perfect sphere. It wants to crush the cloud into a single point. But the spin fights back. Material falling from the poles, the top and bottom of the spinning cloud, can fall straight down. There is nothing to stop it. It rains down onto the center. But material falling from the sides, from the equator, feels a new force, centrifugal force. The spin pushes it outward. It is like riding a merry-go-round. You feel a force pushing you away from the center. The gas at the equator feels this push. It fights against gravity. It cannot fall straight in. Instead, it spirals. It settles into an orbit. The result is a flattening. The spherical cloud is squashed. It transforms into a disk, the protoplanetary disk. This is why our solar system is flat. This is why all the planets orbit the Sun in the same plane and in the same direction. We are living on the fossilized remnants of that initial spin. The geometry of our home was decided 4.5 billion years ago by the physics of a falling cloud. Let us move to the center of this disk, the eye of the storm. Here, the material from the poles is crashing down with unchecked violence. The density is skyrocketing. The atoms are being packed closer and closer together. In the open cloud, a hydrogen atom might travel for years before hitting another atom. But here, in the crushing center, collisions are constant. They are happening billions of times a second, and every collision produces heat. This is the transformation of energy. The energy of the fall is turning into the energy of heat. The center of the cloud begins to warm up. It rises from the deep freeze of interstellar space, minus 200 degrees, minus 100, 0. For a long time, this heat can escape. The gas is still thin enough that it is transparent to infrared light. The heat generated by the friction of the falling gas radiates away into the cold void. The core stays relatively cool, allowing gravity to continue crushing it. But there comes a tipping point, a moment of opacity. The gas becomes so dense, so thick, that the infrared light can no longer get out. The photons of heat are trapped. They bounce back and forth between the atoms, heating the gas further. This creates a greenhouse effect of cosmic proportions. The heat is trapped inside the collapsing core. The temperature spikes violently. It jumps to thousands of degrees. The pressure rises. Suddenly, the collapse stops. The internal pressure of the hot gas becomes strong enough to push back against the weight of the gravity. The freefall is arrested. A stable, hydrostatic object has formed. A protostar is born. This is the infant sun. It is not yet a star. In the true sense, it is not burning nuclear fuel. There is no fusion happening in its core. It is powered entirely by gravity. It shines only because it is being crushed. It glows like a horseshoe being hammered on an anvil. It is immense. This proto-sun is enormous, dozens of times larger than the sun we see today. It is bloated, red, and turbulent. Its surface is boiling. It is a chaotic ball of superheated gas, pulsing and trembling as it tries to find its shape. If you could see it, it would look like a deep red coal in a dark fire. It emits mostly infrared light, heat radiation. It is hidden from the rest of the galaxy inside the dusty cocoon of the nebula. It is an incubator. But the feeding is not over. The protostar is still growing. Material from the disk is still spiraling inward, raining down onto the surface of the star. This rain of matter is violent. The gas strikes the surface of the protostar at supersonic speeds, creating shock waves that heat the surface to blazing temperatures. The star is eating its own cradle. As the star spins, it generates a magnetic field. The plasma, charged gas, creates a dynamo. Powerful magnetic lines of force erupt from the surface of the young sun. They twist and tangle, wound up by the rapid rotation. These magnetic fields act like cannons. They channel some of the infalling gas away from the star. Instead of falling onto the equator, some of the gas is caught by the magnetic field lines and flung out from the poles. Huge jets of gas blast out from the north and south poles of the infant sun. These are bipolar outflows. They travel at hundreds of kilometers per second, piercing the surrounding nebula. These jets are the clearing mechanism. They punch a hole in the cocoon. They push the remaining cold gas away. they allow the star to be seen. If we looked at the sun at this stage from a distance, it would look like a lighthouse, sweeping beams of matter into the dark. This phase of life is known to astronomers as the T Tauri phase. It is the adolescence of the star. It is a time of temper tantrums. The young sun is unstable. It flares wildly. Its brightness can change by a factor of 10 in a single week. It blasts the surrounding space with intense X-rays and ultraviolet light. It is a dangerous, violent neighbor. But this violence is necessary. The strong solar wind blowing from the T Tauri star begins to clear the solar system. It strips the gas away from the inner planets. It ensures that Earth will be a rocky world, not a gas giant. It sets the boundaries of our home. But deep inside, in the core of the protostar, the pressure is building. The weight of the outer layers is crushing the center. The protostar is shrinking. This is the Kelvin-Helmholtz contraction. As the star shrinks, it releases gravitational potential energy. This energy turns into heat. The core gets hotter and hotter. The temperature climbs. 2,000 degrees, 10,000 degrees, 50,000 degrees. The atoms are moving so fast that they strip off their electrons. The gas becomes a plasma, a soup of nuclei and electrons swimming freely. But it is still not hot enough. To ignite a star, you need millions of degrees. You need to overcome the fundamental forces of nature. Protons are positively charged. They repel each other. It is the electromagnetic force. It pushes them apart. To fuse them, to stick them together, you have to smash them together so hard that they overcome this repulsion. You need immense speed. You need immense heat. The young sun is trying to get there. It is squeezing itself. It is trading size for heat. For millions of years, this contraction continues. The sun gets smaller, denser, and hotter. It is a slow, grinding compression. While the sun struggles to ignite, the disk around it is evolving. The dust grains are sticking together. They are building the planets. We must remember that the sun contains 99.8% of the mass of the solar system. All the planets, all the moons, all the asteroids and comets combined are just the 0.2%. They are the leftovers, the crumbs from the banquet. But these crumbs are undergoing their own drama. In the heat near the star, dust grains of iron and rock collide and fuse. They form pebbles, then boulders, then planetesimals, mountains floating in space. Further out, beyond the frost line, where the sun's heat is too weak to melt ice, the building blocks are different. There, water freezes, ammonia freezes, methane freezes. The planets there are built of ice and gas. They grow huge. Jupiter and Saturn are born in the cold dark, gathering the gas that the inner planets could not hold. The architecture of the solar system is being laid down. The hot inner zone for rock, the cold outer zone for gas, all dictated by the temperature of the glowing red ball in the center. But the sun is still waiting. It is waiting for the spark. It has been contracting for 10 million years. It has shrunk from the size of the solar system to a size only a few times larger than it is today. The core temperature reaches 1 million degrees. Not enough. The core temperature reaches 5 million degrees. Still not enough. The protons are moving fast, rushing toward each other, but at the last moment, they veer away, repelled by their positive charges. They bounce. Gravity pushes harder. It adds more weight. The density increases. The atoms are packed so tight they are almost touching. Finally, the temperature crosses a critical threshold, 10 million degrees Kelvin. At this temperature, the protons are moving at a significant fraction of the speed of light. They are buzzing with kinetic energy. And something else comes into play: quantum mechanics. As we will see in the next chapter, the laws of the classical world break down. The protons stop acting like solid balls and start acting like waves. They begin to tunnel through the barrier that holds them apart. But for now, in this chapter, we stand on the brink. The sun is fully formed in terms of mass. It has gathered all the material it will ever have. It has cleared its neighborhood. It stands alone in the center of the disk. It is a dark star, a brown dwarf in waiting. If it stops shrinking now, if it doesn't get any hotter, it will be a failed star. It will glow dimly for a few billion years and then fade into blackness. It will be a Jupiter-like object drifting in the void. But the sun is heavy enough. It has the mass. Mass is destiny in the world of stars. Because it is heavy, gravity is strong. Because gravity is strong, the pressure is high. Because the pressure is high, the heat is inevitable. The ignition is not a matter of chance. It is a matter of time. The fuse is burning. Imagine floating in the disk, looking at this pre-ignition sun. It covers a huge part of the sky. It is a churning, angry sphere of orange and red. It doesn't have a sharp edge. Its atmosphere bleeds into the space around it. Huge sunspots, thousands of times larger than the ones we see today, drift across its surface. Flares brighter than the star itself erupt, bathing the disk in harsh light. It is a violent, unstable, terrifying object. It is also shrinking. Every day, it gets a little smaller. Every day, the noose of gravity tightens around the core. We are witnessing the final squeeze, the moment before the miracle. The universe is about to switch from a chemical engine to a nuclear engine. In the next chapter, we will dive into the very center. We will enter the quantum realm. We will see the moment when the strong nuclear force, the force that holds the nucleus together, snaps shut. We will see the first conversion of mass into energy. Rate 100%, pitch 1%. We will watch the sun turn on. We will see the shockwave of ignition. We will see the main sequence begin. But for now, stay in the anticipation. The heat is rising. The pressure is building. The potential is limitless. The dark cloud has become a glowing sphere. The sphere is becoming a star. Rest in the warmth of the compression. The fire is coming. We are deep within the crushing heart of the protostar. The temperature has climbed to 10 million degrees. The pressure is billions of times greater than the atmosphere of Earth. The atoms are screaming. They are stripped of their electrons, reduced to naked nuclei, rushing past each other at a significant fraction of the speed of light. For millions of years, gravity has been the master. It has squeezed the cloud of gas into a ball, smaller and smaller, trading space for heat. But now, gravity has met its match. It has pushed matter to the very edge of what is possible. It has pushed the protons so close together that they can feel each other's breath. In the classical world, the world of everyday physics, this is where the story would end. The protons are positively charged. They repel each other with a ferocity that grows infinitely strong. As the distance shrinks to zero, they should bounce. They should never touch. The star should be a dead, hot ball of gas, slowly cooling into oblivion. But in the quantum world, the rules are different. A proton is not a hard sphere. It is a wave. It is a smear of probability, and because it is a wave, it doesn't have a hard edge. It can be in two places at once. As two protons rush toward each other, their waves overlap. There is a tiny, vanishingly small chance that one proton can simply appear inside the other, bypassing the electric wall entirely. This is quantum tunneling. It is the ghost in the machine. In the core of the Sun, this event is incredibly rare. For any individual proton, it might happen once in 10 billion years, but there are septillions of protons here. The law of large numbers takes over. Somewhere in the dense churning plasma, two protons tunnel. They touch. Instantly, the strong nuclear force snaps shut. This is the force that holds the universe together. It is 100 times stronger than electricity, but it only works at a range of a femtometer, the width of a nucleus. It grabs the two protons and fuses them. But two protons cannot stay together. They are unstable. In a flash of weak nuclear decay, one proton turns into a neutron, spitting out a positron and a neutrino. The positron, a particle of antimatter, immediately hits an electron and annihilates, releasing a burst of gamma rays. The neutrino, a ghost particle, flies straight out of the Sun, passing through the star as if it weren't there. What remains is deuterium, heavy hydrogen, a proton and a neutron bound together. This deuterium is hungry. It barely lasts a second before another proton slams into it. They fuse. Now we have helium-3, two protons, one neutron. Finally, two helium-3 atoms find each other in the crush. They smash together. They form helium-4, two protons, two neutrons, and eject two spare protons back into the mix to start the cycle again. This is the proton-proton chain. It is the alchemy of the stars. It turns hydrogen into helium. But the most important part is the weight. The resulting helium-4 nucleus weighs slightly less than the four protons that made it. About 0.7% of the mass has vanished. It has ceased to be matter. It has become energy. Einstein's equation, E = mc2, tells us the exchange rate. A tiny amount of mass creates a massive amount of energy. The missing mass is released as a photon of high-energy gamma radiation. This single reaction produces a microscopic amount of energy. But in the core, it is happening 10 to the power of 38 times every second. The energy release is cataclysmic. It creates an outward pressure, a thermal wind. For the first time in history, there is a force strong enough to fight gravity. The collapse stops. The star shudders. The inward fall of the gas hits a wall of nuclear fire and bounces. The star inflates. It stabilizes. Hydrostatic equilibrium is achieved. The weight of the star pushing down is exactly balanced by the pressure of the fusion pushing up. The Sun has become a main sequence star. It is no longer a dark cloud. It is no longer a glowing ember. It is a self-sustaining fusion reactor. It is turned on. The energy generated in the core begins to work its way out. It is not a quick journey. The core is so dense that light cannot travel in a straight line. The gamma-ray photons bounce, scatter, and zigzag. They are absorbed and re-emitted trillions of times. It can take 100,000 years for a photon to travel from the center to the surface. The light hitting your eyes today was generated when humans were just learning to make stone tools. It is ancient light. But as it travels, it changes. The deadly gamma rays lose energy with every bounce. They stretch out. They become X-rays, then ultraviolet, then visible light. By the time they reach the surface, the photosphere, they are a gentle yellow-white glow. This surface is boiling. The heat from below rises in giant convection cells, granules the size of Texas. Hot gas rises, releases its light into space, cools, and sinks back down. The face of the sun is a shifting mosaic of liquid fire. And what of the solar system? The ignition of the sun changes everything. When the nuclear fire turns on, the sun wakes up. It blasts out a wind, the solar wind, a stream of charged particles, protons and electrons moving at 1,000,000 miles an hour. This wind sweeps through the solar system. It acts like a broom. For millions of years, the space between the planets has been filled with gas and dust, a thick fog. But the solar wind blows it away. It strips the gas from the inner solar system, leaving the rocky planets, Mercury, Venus, Earth, Mars, naked in the void. It pushes the gas outward, past the asteroid belt to where the giants live. Jupiter and Saturn have already gathered their atmospheres, so they are safe. But the loose gas is banished to the interstellar medium. The view clears. For the first time, the planets can see the stars. The nebula is gone. The solar system is transparent. The sun is now a stable, shining beacon. But it was not always so kind. The young sun, the zero-age main sequence sun, was spinning fast. It rotated once every few days. Today, it takes a month. This rapid spin created a powerful magnetic dynamo. The young sun was covered in star spots. It flared constantly. It bathed the young Earth in intense X-rays and ultraviolet light. It was a paradox. The young sun was actually dimmer than today, about 30% dimmer in visible light, but much more violent in high-energy radiation. This faint young sun presents a puzzle. If the sun was dimmer, why didn't the Earth freeze? We know there was liquid water on Earth very early. The answer likely lies in the Earth's own atmosphere, a thick blanket of greenhouse gases that kept the planet warm despite the weak star. But the violence of the young sun also helped. The solar flares may have provided the energy needed to knit complex molecules together on Earth. The lightning of the solar storms may have sparked life. The sun also began to slow down. The solar wind carries mass away from the star. As the mass leaves, it carries angular momentum. It acts like a brake. Over billions of years, the sun spun down. It calmed. The magnetic storms became less frequent. It settled into the steady, middle-aged rhythm we know today, a quiet yellow dwarf. But inside, the clock is ticking. The sun is a machine that consumes its own parts. Every second, it burns 600 million tons of hydrogen. It turns it into 596 million tons of helium. The difference, 4 million tons, is lost. The sun is getting lighter. Its gravity is getting slightly weaker. The Earth's orbit is spiraling outward by a tiny fraction of an inch every year. And the core is changing. As hydrogen is used up, it is replaced by helium ash. The helium is heavier. It sinks to the very center. This helium core is dead weight. It does not fuse. Not yet. It just sits there, getting hotter and denser. To support this dead weight, the hydrogen-burning shell around it has to work harder. It burns hotter. This means the sun is getting brighter, very slowly, about 10% every billion years. This brightening will eventually seal the fate of life on Earth, but that is a story for the far future. For now, the balance holds. Let us look at the sun not just as a physics experiment, but as a parent. The sun's gravity herds the planets. It keeps them in line. It protects them. The heliosphere, the bubble of solar wind, extends far out beyond Pluto. It pushes back against the cosmic rays of the galaxy. It creates a safe harbor in the interstellar storm. Within this harbor, the planets have evolved. Mercury, baked to a cinder. Venus, boiled dry. Mars, frozen and rusted. And Earth. Earth sitting in the Goldilocks zone. Not too hot, not too cold. Just right for liquid water. Just right for chemistry. Just right for us. We are the children of the sun's stability. If the sun were a larger star, it would have burned out in a few million years, long before life could start. If it were a smaller red dwarf, it would flare violently, stripping our atmosphere. We won the cosmic lottery. We orbit a G-type star, stable, long-lived, metal-rich. As we close this chapter, float in the clear space of the new solar system. The dust is gone. The planets are polished gems orbiting in the black. In the center, the white-hot spark has become a steady golden ball. It bathes the system in a constant wash of photons. Feel that light on your face. It is the same light that fell on the first oceans, the same light that fed the dinosaurs, the same light that powers the wind and the rain. It is the energy of the Big Bang, stored in hydrogen, released by gravity, and delivered to you. In the next chapter, we will look at the sun's influence on the Earth. We will look at the seasons, the day and night cycle, the way the sun drives the biosphere. We will see how photosynthesis captures this nuclear fire and turns it into green sugar. We will see how the sun is not just up there, but inside us. But for now, rest in the knowledge that the fire is lit, the engine is running, the lights are on. The long cold of the nebula is over. The age of sunlight has begun. We have witnessed the ignition. Deep in the core, the nuclear fires have been lit. The sun has transitioned from a collapsing cloud of gas into a self-sustaining star. It has achieved the balance of the main sequence, but the birth of a star is not a tidy event. It is a messy, violent, and chaotic process. The young sun sits in the center of a vast, swirling disk of leftovers. This is the solar nebula, the debris field of dust and gas that did not make it into the star. It is a thick, opaque fog that fills the solar system from the orbit of Mercury out to the edge of the void. To an observer on a young planet, there would be no stars at night. There would only be the hazy glow of the disk, scattering the light of the infant sun. But the sun is waking up, and like any newborn, it is crying out. It begins to clear its cradle. This phase of the sun's life is known as the T-Tauri phase. It is named after a variable star in the constellation Taurus, which serves as the archetype for all young, low-mass stars. In this phase, the sun is not the steady, calm, yellow orb we see today. It is a tempestuous, magnetic monster. It is spinning wildly. Today, the sun rotates once every 25 days, but in its youth, it spun once every 3 or 4 days. This rapid rotation acts as a dynamo. It whips the magnetic field lines of the star into a frenzy. They twist, tangle, and snap, releasing immense amounts of energy. The surface of the young sun is covered in massive star spots, dark, magnetic storms that can cover half the face of the star. These magnetic storms launch flares of X-rays and ultraviolet light that are hundreds of times more powerful than anything we experience now. But more importantly, they launch matter. They drive a ferocious wind. This is the primordial solar wind. It is a stream of protons and electrons blasted off the surface of the star at supersonic speeds. It is a gale of plasma, and it begins to sweep through the solar system like a broom. For millions of years, gravity had been pulling material in. It was gathering the gas toward the center. But now, the pressure of the light and the force of the wind begin to push out. The tide turns. The wind strikes the inner edge of the protoplanetary disk. It hits the hydrogen and helium gas that is floating between the growing rocky planets. The gas is light. It is easily moved. The wind strips it away. Molecule by molecule, the fog is blown out into deep space. The inner solar system, where Mercury, Venus, Earth, and Mars are struggling to form, is scrubbed clean. The gas that might have turned Earth into a gas giant is removed. We are left with only the heavy materials, the rock and the metal, that are too dense to be blown away. This clearing process is crucial for the destiny of the planets. If the gas had remained, the rocky planets would have grown thick, crushing atmospheres of hydrogen, choking off any possibility of liquid oceans or surface life. The violence of the young sun saved us from suffocation. As the wind pushes outward, it encounters a boundary, a line in the sand drawn by temperature. This is the frost line, or the snow line. Close to the sun, within this line, it is too hot for volatile compounds like water, ammonia, and methane to exist as solids. They vaporize, they become gas, and the solar wind blows them away. This is why the inner planets are small and rocky. They are made of the dry leftovers, silicates and iron. But beyond the frost line, somewhere between the orbits of Mars and Jupiter, the temperature drops low enough for these compounds to freeze. Water becomes ice. Methane becomes snow. Out here, the solar wind is weaker. The cold protects the material. Solid ice is abundant. In fact, there is far more ice than rock. This abundance of building material allows the planets in the outer dark to grow huge. Jupiter and Saturn formed here. They started as massive cores of ice and rock, 10 times the mass of Earth. Because they grew so big, so fast, they had enough gravity to hold on to the hydrogen and helium gas before the sun could blow it away. They became gas giants. They are captured pieces of the original solar nebula, preserved in the deep freeze. They are failed stars in their own right, wrapped in thick blankets of primordial atmosphere. The solar wind pushes against these giants, but they are too heavy to be moved. The wind flows around them, stripping away the loose gas between their orbits, defining the lanes of the solar system. It carves the grooves in the record. Further out, Uranus and Neptune form. They are the ice giants. They formed later and slower. By the time they were big enough to grab gas, the sun had already blown most of it away. They missed the banquet. They are smaller, colder, composed mostly of water, ammonia, and rock, with only a thin skin of hydrogen. This era of clearing takes about 10 million years. It is a blink of an eye in cosmic time, but it is the formative youth of the system. As the gas disappears, the drag disappears. In the early days, the friction of the gas caused the planets to migrate, to spiral inward toward the sun. But as the wind clears the fog, the vacuum takes over. the planets settle into stable orbits. The migration stops. The architecture of the solar system is locked in, but the sun is doing more than just blowing. It is breaking. We mentioned that the young sun was spinning incredibly fast. If it had kept spinning that fast, it would have been unstable. It might have flung itself apart. But the solar wind acts as a brake. Imagine a figure skater spinning on ice. If she throws her arms out, she slows down. The solar wind is the sun throwing its arms out. As the charged particles leave the surface, they are still tethered to the sun by the magnetic field. The magnetic field lines act like stiff spokes on a wheel, extending millions of miles into space. The particles slide out along these spokes. As they get further out, they act like a drag chute. They steal angular momentum from the star. This magnetic braking slowly robs the sun of its spin. Over billions of years, the rotation slows from once every 3 days to once every 25 days. The frantic energy of youth settles into the steady, majestic rotation of adulthood. The magnetic field calms down. The star spots shrink. The flares become less frequent. The sun transitions from the violent T Tauri phase to the stable main sequence phase. It becomes the quiet, reliable provider of energy that we know. But the debris is not entirely gone. The major planets have formed, but there is still rubble. Billions of leftover planetesimals, asteroids, and comets litter the system. The clearing of the gas destabilizes these small bodies. Without the gas to dampen their movements, they are tugged by the gravity of the giant planets. They begin to fly around in chaotic orbits. Many are thrown inward. They rain down on the inner planets. This is the late heavy bombardment. The craters on the moon are the scars of this time. But this bombardment is a gift. The Earth, forming in the hot zone, was dry. It had lost its water to the heat. But the comets coming from the outer solar system, thrown by Jupiter, guided by the sun's gravity, were made of ice. They smashed into the young Earth, vaporizing on impact, releasing oceans of steam into the atmosphere. The water you drink today, the water in your cells, was delivered by these cosmic icebergs. It is a gift from the frost line, brought to us by the gravity of the cooling system. Other debris was thrown outward. The solar wind and the gravity of the giants pushed trillions of icy rocks to the very edge of the sun's influence. They formed a vast, spherical shell surrounding the solar system, the Oort cloud. This is the deep freeze. The Oort cloud extends almost a light year into space. It is the limit of the sun's gravity. These objects drift in the dark, barely holding on to their orbit, occasionally nudged by a passing star to fall back in as long-period comets. Between the rock of the inner system and the ice of the outer system, the asteroid belt remained. It is a ring of debris that couldn't form a planet because of Jupiter's gravity. It is a museum of the early solar system. The asteroids are the original building blocks. They are the time capsules. By studying them, we can see the chemistry of the dust before it was melted and differentiated into worlds. We can touch the raw material of the nebula. As the dust cleared, the sunlight changed. In the beginning, the light had to fight its way through the fog. It was scattered, diffuse, and red. But as the wind swept the space clear, the light became sharp. Shadows appeared for the first time. The vacuum became transparent. The stars of the Milky Way became visible from the surface of the planets. The solar system opened its eyes to the universe. The sun itself looks different now. It has settled into a rhythm. Its core is fusing hydrogen into helium at a steady rate, 600 million tons every second. The pressure of the light pushing out balances the gravity pulling in. This balance is incredibly stable. It will hold for 10 billion years. It provides a habitable zone, a ring of space around the star where the temperature is just right for liquid water. In the early days, this zone was shifting, but as the sun stabilized, the zone locked into place. Earth sits squarely in the middle of it. Venus is too close. Mars is on the edge. We are in the sweet spot. But the sun is not static. It is evolving even now. As it burns fuel, the core shrinks slightly and gets hotter. This makes the nuclear reactions run faster. The sun is slowly getting brighter. When it was born, it was about 70% as bright as it is today. It was a faint young sun. This presents a puzzle. If the sun was dimmer, why didn't the early Earth freeze solid? The answer lies in the Earth's own atmosphere, a blanket of greenhouse gases that kept the heat in. The planet and the star have evolved together, compensating for each other's changes to maintain a home for life. The solar wind continues to blow today, but it is a gentle breeze compared to the gale of the T Tauri phase. It creates the heliosphere, a bubble of magnetic influence that protects the solar system from the high-energy cosmic rays of the galaxy. We are living inside the atmosphere of the sun. The aurora borealis, the northern lights, is the visible interaction of this wind with our planet. It is the ghost of the T Tauri gale, still brushing against our world. The sun also has a heartbeat. The solar cycle. Every 11 years, its magnetic field flips. Sunspots appear and disappear. Flares erupt. It is a reminder that the dynamo inside is still spinning, still churning, still alive. But the violence is contained. The sun is a benevolent dictator. It holds the planets in line with gravity, feeds them with light, and protects them with wind. As we look at the cleared solar system, we see a masterpiece of order. The planets move in ellipses, obeying Kepler's laws. The moons tick around the planets. The comets dive and return. It is a clockwork mechanism, wound by gravity and lubricated by the vacuum. But it was forged in chaos. The piece we see today is the survivor of 1 billion collisions. Every crater on the moon is a testament to the clearing process. Every drop of water in the ocean is a survivor of the Great Migration. In the next chapter, we will look at the legacy of this light. We will look at how the sun's energy drives the systems of the Earth. We will see how the differential heating of the equator and the poles creates the wind and the weather. We will see how the sun lifts water from the ocean to create rain. We will see how it powers the biosphere through the green miracle of photosynthesis. We will explore the Goldilocks zone in more detail and ask what happens when a star is too hot or too cold. We will appreciate the specific, delicate qualities of our G-type yellow dwarf. For now, imagine the solar system in those early days of clarity. The dust has settled, the fog has lifted, the sun hangs in the black sky, a perfect, dazzling sphere. The planets are new, polished, and waiting. The stage is set for the next act of the cosmic drama. Life. rest in the quiet of the vacuum. The storm has passed. The light is clear. The violent tantrums of the T-Tauri phase have ended. The great winds that scoured the solar system have quieted to a steady breeze. The dust has settled, and the planets have found their grooves in the dark. In the center of it all, the sun has achieved the holy grail of stellar physics, hydrostatic equilibrium. It has entered the main sequence. This is the long, golden summer of a star's life. For the next several billion years, the sun will not change its shape or its size. It has found the perfect balance between the crushing weight of gravity pulling inward and the explosive pressure of nuclear fusion pushing outward. It is a stable, self-regulating fusion reactor, suspended in the void. But stability does not mean stillness. The sun is still a roaring ball of plasma, 800,000 miles wide. It is still consuming 600 million tons of hydrogen every second. It is just that the violence is now contained. The chaos has been harnessed into a steady stream of light and heat that bathes the solar system. This light is the lifeblood of the planets. It radiates outward in a perfect sphere, diminishing in intensity as it travels. By the time it reaches the Earth, 93 million miles away, it has spread out enough to be gentle. It is no longer the sterilizing blowtorch of the protostar. It is a warm embrace. However, the sun of the early Earth was not the same as the sun of today. When the sun first settled onto the main sequence, 4.5 billion years ago, it was smaller and cooler. It shone with only 70% of its current brightness. This is known as the faint young sun. This dimness presents a puzzle that has troubled scientists for decades. If the sun was 30% weaker, the Earth should have been a frozen ball of ice. The oceans should never have formed. The planet should have been locked in a permanent global winter. Yet, the geological record shows us that the early Earth was wet. There were oceans. There was liquid water. How is this possible? How can a planet stay warm under a cold star? The answer lies in the partnership between the Earth and the sun. The Earth wrapped itself in a blanket. The primordial atmosphere was rich in greenhouse gases, carbon dioxide, methane, and water vapor, outgassed by the violent volcanoes of the Hadean Eon. These gases trapped the meager heat of the young sun, holding it close to the surface. The planet compensated for the star. As the sun slowly brightened over billions of years, the Earth's biology slowly removed the greenhouse gases, thinning the blanket just as the fire got hotter. It is a cosmic dance of regulation that has kept our home habitable for 4 billion years. Pitch 1%. This habitability is defined by a specific region of space, the Goldilocks zone. This is the narrow ring around a star where water can exist as a liquid. Too close, and the water boils away into steam. Too far, and it freezes into ice. Earth sits squarely in the middle of this zone, but it is a precarious position. Look at our neighbors. Venus sits just inside the inner edge. It received slightly too much sunlight. Its oceans evaporated, creating a runaway greenhouse effect that turned the planet into a hellscape, hot enough to melt lead. Mars sits on the outer edge. It was too small to hold its atmosphere. Its water froze and retreated underground. We are the survivors. We are the ones who stayed in the sweet spot. But the Goldilocks zone is not static. As the sun continues to burn fuel, its core shrinks and heats up, making the star brighter. The habitable zone is slowly moving outward. In 1 billion years, Earth will be on the hot edge. But for now, in this epoch, the balance holds. Let us look at how this solar energy drives the systems of our world. The sun is the engine of the Earth's climate. It does not heat the planet evenly. It strikes the equator directly, delivering intense heat, while it glances off the poles at a shallow angle, delivering very little. This inequality creates a massive heat engine. The atmosphere tries to fix the imbalance. Hot air at the equator rises, carrying moisture. It travels toward the poles, cooling and sinking. This movement creates the trade winds, the westerlies, and the jet streams. Every gust of wind you feel on your face is driven by the sun. Every storm, every hurricane, every gentle breeze is simply the atmosphere trying to move solar heat from one place to another. The sun is the conductor of the weather. It also drives the water cycle. Solar photons strike the surface of the ocean. They transfer their energy to the water molecules, causing them to vibrate until they break free of the liquid. Evaporation. The sun lifts billions of tons of water into the sky every day. It carries this water over the continents and releases it as rain. Without the sun, the water would be frozen and static. The rivers would stop flowing. The planet would be motionless. The sun is the pump that keeps the fluids of the Earth circulating. But the most profound connection between the star and the planet is not the wind or the rain. It is life. Deep in the cells of every green plant, there is a molecule called chlorophyll. It is a magical structure, shaped like a net to catch photons. When a particle of light from the sun, a particle that has traveled 100,000 years to get out of the core and 8 minutes to cross space, hits this molecule, it is captured. The energy of the photon is used to split water and carbon dioxide, forging them into sugar. This is photosynthesis. It is the process of turning starlight into matter. Every leaf is a solar panel. Every forest is a battery charging up on solar energy. When you eat an apple, you are eating stored sunlight. When you burn wood, you are releasing the heat of the sun that was captured years ago. When you drive your car, you are burning ancient sunlight trapped by algae millions of years ago. The entire biosphere is a solar-powered machine. We are all creatures of the sun, woven from light and air. But the sun does more than feed us. It protects us. The solar wind, that stream of charged particles blowing outward from the star, does not stop at Earth. It continues outward, past Mars, past Jupiter, past Pluto. It blows a vast bubble in the interstellar medium. This bubble is the heliosphere. It extends more than 10 billion miles into space. Inside this bubble, space is dominated by the sun. Outside, it is dominated by the cold, thin wind of the galaxy. The galaxy is a dangerous place. It is filled with high-energy cosmic rays, shrapnel from exploding stars, and supermassive black holes. These rays are lethal. They can shred DNA and strip away atmospheres. But the heliosphere acts as a shield. The pressure of the solar wind pushes back against the cosmic rays, deflecting most of them away from the solar system. The sun creates a safe harbor, a calm eddy in the violent river of the galaxy. Without this protective bubble, complex life on Earth might never have evolved. Yet the sun is not a static bulb. It breathes. It has a heartbeat. If you watch the sun over years, you see it change. The face of the star breaks out in dark blemishes, sunspots. These are islands of magnetism, regions where the sun's magnetic field becomes so twisted and strong that it stops the heat from rising to the surface. The number of spots rises and falls in a regular rhythm, the solar cycle. Every 11 years, the sun's magnetic poles flip. North becomes south. South becomes north. At the beginning of the cycle, solar minimum, the sun is quiet. Its face is blank. But as the years pass, the rotation of the star twists the magnetic fields like rubber bands. They tangle and knot. Sunspots appear. The star becomes active. During solar maximum, the sun is a tempest. It hurls flares of X-rays into space. It launches coronal mass ejections, billion-ton clouds of plasma that crash through the solar system. Rate 100%, pitch 1%. When these storms hit Earth, they do not kill us thanks to our own magnetic field. Instead, they create beauty. The solar particles funnel down toward the poles, slamming into the atmosphere. They excite the oxygen and nitrogen atoms, making them glow. The aurora borealis and aurora australis are the visible signs of the sun's mood. Green curtains of light dancing in the winter sky are the fingerprints of a magnetic storm 93 million miles away. It is the sun reaching out and touching the Earth. This cycle has been beating for billions of years. We see evidence of it in the growth rings of ancient trees and the ice cores of Antarctica. The Earth feels the rhythm of its parent star. Sometimes the sun goes quiet for longer periods. In the 17th century, the sunspots vanished for 70 years. This was the Maunder minimum. It coincided with the Little Ice Age on Earth. The Thames River in London froze solid. The winters were brutal. It is a stark reminder that our climate is tethered to the furnace in the sky. But despite these fluctuations, the sun is remarkably stable. It is a G-type main sequence star. This is the most reliable type of star in the universe. Red dwarfs, the most common stars, are volatile. They flare violently, doubling in brightness in minutes, potentially sterilizing their planets. Blue giants burn out in a few million years, dying before life has a chance to start. Our yellow sun is the perfect middle ground. Bright enough to warm us, calm enough not to kill us, and long-lived enough to allow evolution to work its slow magic. We won the cosmic lottery with this star. Let us float here for a moment, basking in the stability of the main sequence. Imagine the sun as it is right now, a sphere of boiling plasma, singing with sound waves, threaded with magnetism. It looks still from a distance, but up close, it is a landscape of geysers and canyons of fire. The spicules on the surface are jets of gas as tall as continents, rising and falling in minutes. The prominences are loops of glowing gas that arch high into the black sky, large enough for the Earth to pass through. And surrounding it all is the corona, the sun's atmosphere, a ghostly white halo of plasma that extends millions of miles into space. It is hotter than the surface, 1,000,000 degrees, a mystery that physicists are still trying to solve. It is the crown of the king. This is the environment that holds us. We are not floating in empty space. We are floating in the outer atmosphere of a star. We are inside the sun's domain. The gravity of the sun is the anchor of our lives. It grips the Earth, swinging it around at 67,000 miles per hour. It holds the solar system together against the centrifugal force of the galaxy. Without this gravity, the Earth would fly off into the interstellar dark, a rogue planet freezing in the void. The sun is the tether, it is the hearth. But even the main sequence must end. The sun is a machine that consumes its own parts. It has a fuel tank and the gauge is moving. Every second, 4 million tons of matter vanishes. The sun is getting lighter. As it gets lighter, its grip on the planets loosens slightly. The Earth drifts outward by about a centimeter a year. And deep in the core, the ash is building up. The helium produced by fusion is settling in the center. It is dead weight. It does not fuse. It just sits there, getting hotter and denser. To support this heavy core, the sun has to work harder. The fusion reactions speed up. The sun is slowly getting brighter. In a billion years, it will be 10% brighter than it is today. This brightening is the ultimate clock of life on Earth. Eventually, the heat will be too much. The oceans will evaporate. The biosphere will retreat. The story of life on Earth will end, not with a bang, but with a slow drying out under the glare of an aging star. But that is a story for the distant future. Today, the sun is in its prime. It is halfway through its life. It has 5 billion years of fuel left. It has 5 billion years of sunrises to give us. As we prepare for the final chapter of our journey, we must look ahead. We must see what happens when the fuel finally runs out. In the next chapter, we will travel 5 billion years into the future. We will witness the death of the sun. We will see it swell into a red giant, swallowing Mercury and Venus, turning the Earth into a molten cinder. We will see the gentle shedding of its outer layers, creating a beautiful planetary nebula, a cosmic flower marking the grave of the solar system. And we will see what remains: the white dwarf, the diamond in the dark, the cooling ember that will drift through the galaxy forever. For now, feel the gratitude for the yellow star. Feel the warmth on your skin and your memory. It is a faithful companion. It rises every day. It chases away the dark. It feeds the world. You are here because the star is here. You are safe in the light of the main sequence. We have watched the sun ignite from a cold, dark cloud. We have seen it clear the solar system with its T-Tauri winds. We have seen it settle into the long, golden stability of the main sequence. But no fire burns forever. The fuel tank is finite. The clock is ticking. Tonight, we look forward. We travel billions of years into the future to witness the final act of our star. It is a story of transformation, of beauty, and of a quiet, lingering end. Currently, the sun is about halfway through its life. It has been burning for 4.5 billion years, and it has about 5 billion years left of hydrogen fuel. It is in its prime. It is stable. But deep in the core, a change is happening. As the hydrogen atoms are fused into helium, the helium ash builds up. It is heavier than the hydrogen. It sinks to the very center. This helium core is inert. It does not fuse. It sits there, a growing ball of dead weight in the heart of the star. As it grows, it gets denser. Its gravity pulls the surrounding hydrogen inward. This compression heats up the hydrogen shell around the core. The nuclear reactions speed up. The sun burns hotter. This means that the sun is slowly getting brighter. It is brightening by about 10% every billion years. This sounds slow, but over geological time it is relentless. In about 1 billion years, the extra heat will reach Earth. It will push the planet out of the Goldilocks zone. the oceans will begin to evaporate. The water vapor, a potent greenhouse gas, will trap even more heat. The Earth will become a steam bath. Complex life, plants, animals, us, will not survive this shift. The biosphere will retreat back into the microbial world, hiding in deep caves and under the last remaining pools of water. The surface will become a desert. But the sun is not done. In 5 billion years, the hydrogen in the core will be exhausted. The fuel gauge hits empty. The hydrostatic equilibrium, the balance between gravity and fusion, is broken. Gravity wins. The core collapses. It shrinks rapidly, heating up as it falls. But this collapse releases immense amounts of gravitational energy. This energy floods into the outer layers of the sun. The envelope of hydrogen gas swells. The sun begins to grow. It expands outward. It swallows the orbit of Mercury. It swallows the orbit of Venus. It becomes a red giant. From the Earth, the sun will look terrifying. It will span a huge portion of the sky, a wall of angry red fire, looming over the horizon. It will be 2,000 times brighter than it is today. The rock of the Earth will melt. The atmosphere will be stripped away by the intense solar wind. The cradle of humanity will be sterilized. But inside the star, a new fire is about to light. The collapsing helium core reaches a critical temperature, 100 million degrees. At this heat, helium atoms can fuse. 3 helium nuclei smash together to form carbon. This is the triple alpha process. It ignites in a flash, the helium flash. The sun finds a second wind. It stabilizes again, burning helium into carbon and oxygen. It shrinks slightly, becoming a horizontal branch star. It lives for another 100 million years on this new fuel. But helium burns fast, much faster than hydrogen. It is a desperate, inefficient fuel. Soon, the helium is gone. Now, the core is made of carbon and oxygen ash. Gravity tries to crush it again, hoping to ignite the carbon. But the sun is too small. It does not have enough mass to fuse carbon. It cannot reach the billion degrees needed. The engine stalls. The outer layers of the sun, loosely held by the distant gravity of the core, begin to drift away. They are pushed out by the pulsations of the dying star. The sun sheds its skin. Layers of glowing gas expand into the solar system. They form a planetary nebula. These are the most beautiful objects in the galaxy: the Ring Nebula, the Helix Nebula, the Cat's Eye Nebula. They are the death shrouds of stars like ours. The gas glows in vivid colors: red for hydrogen, blue for oxygen, green for nitrogen. It is ionized by the exposed core of the star, and what remains? The core. The core has been stripped naked. It is a sphere of ultra-dense carbon and oxygen, about the size of the Earth, but containing half the mass of the sun. It is a white dwarf. It is no longer fusing. It is dead, but it is incredibly hot, 100,000 degrees. It shines with a brilliant white-blue light. It is a diamond in the sky. The density is mind-bending. A teaspoon of white dwarf material would weigh tons. The electrons are squeezed so tight they are touching. This electron degeneracy pressure is the only thing holding the star up against gravity. The white dwarf will sit in the center of the nebula for a few thousand years, lighting up the gas like a neon sign. Then, the gas will drift away. It will merge with the interstellar medium, enriching the galaxy with carbon and oxygen, the seeds of future life. The white dwarf will be left alone. It has no fuel. It cannot generate heat. It can only cool down. It will radiate its stored heat into the vacuum. It will take billions of years. It will turn from blue to white to yellow to red. Eventually, it will become so cold it stops shining. It will become a black dwarf, a cold, dark cinder floating invisible in the void. The universe is not old enough for any black dwarfs to exist yet. Every white dwarf that has ever formed is still shining. Our sun will join them. This is the ultimate fate of our star. Not an explosion, but a slow, peaceful fading, a long retirement. But let us return to the present. Let us return to the yellow sun. It is alive. It is vibrant. It is generous. Every day it lifts the water from the sea to water the land. Every day it feeds the plants that feed us. Every day it drives the wind that cleans the air. It is the father of the solar system. The atoms in your body were not made in the sun. The sun is not hot enough to make iron or calcium, but they were gathered by the sun. The nebula that collapsed to form the sun also formed you. We are the siblings of the star. We are made of the same cloud. As you lie in the dark tonight, feel the warmth of your own body. That warmth is energy. Energy that came from food. Food that came from plants. Plants that caught the light. You are glowing with the light of the sun, released slowly through chemistry. You are a little piece of the star, awake and aware. The sun has set, but it has not gone. It is shining on the other side of the world, waking the day, continuing the cycle. It will be there tomorrow, and the day after, and for 5 billion years to come. It is the most reliable thing in our lives, the constant, the anchor. Rest in that reliability. The universe is holding you. The gravity is holding you. The light is waiting for you. May your sleep be deep, your dreams be bright, and your morning be filled with light. Good night.